Hello and welcome to Team 11's Senior Design Presentation. We are the liquid exhaustion team at Knitline Chemicals, and our members consist of Isaac Bressler, Jenna LaRosa, Margot Blake, Paul Rico, Richard Hoogrider, and myself, Misan Yembra. Our overall goal for this project is to produce styrene from 1,3-butadiene. So for this presentation, we're all going to cover 5 different points. I'm going to be giving some general background information about the plant and the process, and my other teammates are going to be talking about the products that were produced and the specifications that were met, a high-level overview of the production process, an economic analysis indicating the feasibility of the plant, and some recommendations about whether or not we should go forward with this project. Now, our company, Knitline Chemicals, has 3 major locations across the United States. The first one is in Philadelphia, Pennsylvania. The second one is in University Park, Pennsylvania, which is actually the R&D facility that my team and I have been working from to develop the styrene plant for the final location in Houston, Texas. Now, what is great about this Houston, Texas facility is that it has access to many pipelines to supply raw materials and also to possibly transport some of our products. In addition to this, the Houston facility would also be producing C4s as a major byproduct from another process. Now, this C4s is composed of over 52% of 1,3-butadiene, which is essentially the major raw material for our styrene process. Now, based on our calculations and designs that my teammates would discuss further, our plant will produce styrene at a capacity of 974 million pounds per year. This would have a purity of 99.9%, which exceeds the market demands of 99.8%. We will also be producing benzoic acid as a byproduct at a capacity of 26 million pounds per year. This can be sold in the market at 63 cents per pound. Another of our byproducts would be fuel gas, which will be produced at 1,421 million pounds per year and will also be sold in the market. Our final byproduct would be fuel oil. However, this byproduct would not be sold in the market, but it will instead be used as a utility to heat other processes in the plant. Now I'll be handing off the clicker to my teammate Richard, and he's going to talk about the products and some specifications that were met.
First and foremost, we have hard specifications that we have to meet for our plant. All the hard specs for our product are listed here. Were met, meaning a sellable product was produced. The benzoic acid, we will be able to produce benzoic acid as well at 99.7% purity, which meets the hard spec for that product as well. And so this can be sold as a secondary product along with styrene. Other hard specs we met were safety related. The first being the oxygen purity in our process was kept below 60% flammability limit, which meets the company standard. The styrene product storage unit was also kept below 50 degrees Fahrenheit to avoid any kind of exothermic polymerization reactions. There were 3 main soft specs that we did not meet with our design. Each one that we didn't meet was directly related to the waste streams in our process. The overall selectivity of the process and the waste of VCHX and styrene did not meet the spec because of the high percentage of those compounds in the waste streams. Ethylbenzene and styrene are 2 chemicals that are very difficult to separate, so in order to meet the hard spec of 500 ppm of ethylbenzene and the product purity of styrene, a pretty significant loss of styrene was incurred on the styrene purification towers. Also, the production of byproducts such as benzoic acid and ethylbenzene takes away from the overall conversion to styrene. Another soft spec that we didn't meet was the overall energy usage of our distillation columns. The water purification tower that we had in our process uses 11,000 BTUs per pound of product, per pound of styrene product to run. This tower was needed in order to purify the water to avoid cooling water costs as well as wastewater treatment costs. For the environmental impact of our process, we considered 4 main waste streams: fuel oil, fuel gas, low BTU value flare gas, and water vapor. The fuel oil is just a very flammable liquid at atmospheric conditions that we burned in all of our reboilers, completely burned. The fuel gas was also used for fuel, but also sold as a major part of our revenue. The flare gas was combined with excess processed oxygen to make sure that the contaminants were completely combusted in the flare. Overall, our process should not have a very large impact on the environment. Now I'm going to turn it over to Jenna to talk about the process flow.
The base case for our process can be seen on this slide. I'm going to go through each major area and highlight them on the screen so you can see the finer details. So the first area I'm going to highlight is the first half of the process with our reactors. So here you can see the first reactor takes the 1,3-butadiene and converts it into vinyl cyclohexene, or VCHX. From there, it is the VCHX is purified using 2 columns, and then that VCHX is fed into the second reactor to create the styrene product. The next area I'm going to highlight is the recycle around the second reactor. So here you can see there's a series of towers and a flash drum after the second reactor, and the final tower in this series purifies the VCHX to the point that it can be fed into a flash drum, it purifies it more, and then it is fed into the second reactor. This allows us to significantly increase our production of styrene by nearly 9,000 pounds per hour. Finally, the last section I'm going to highlight is the bottom half of the BFD. And this allows us to purify our water stream to the point where it can be vented into the atmosphere, which greatly reduces our operating cost. So that is done by using the LLE column seen and the distillation column labeled water tower. And finally, you can see on this slide benzo towers 1 and 2. This allows us to purify benzoic acid to the point that it is pure enough to sell as an additional product. And now I'm going to pass it off to Margot to talk about economics.
The total capital cost of our plant is $457.75 million. These costs are split between the OBL, IBL, package distillation, and miscellaneous costs. Miscellaneous costs are comprised of things such as spare parts, team costs, contingency, etc. On the board, what you're seeing here is basically a pie chart that shows the different distributions of costs between our different contributions. So the largest, obviously, is our package distillation, which was about 56%. So this was greater than all 3 of the other categories combined. That obviously shows that we have a pretty large cost with our package distillation, which wasn't something that could even be neglected later on, because this could be something that we could end up designing, and that will be something that we will discuss later in our recommendations. Now I'm going to discuss in more detail the IBL and OBL costs. So the IBL costs for our plant, so this consists of capital costs of equipment within battery limit, were $74.08 million. Much of the cost came from distillation towers. As you can see in this pie chart here, this is the largest cost right there. The reason why this cost was so large was because we had a pretty high flow rate, and a lot of our towers needed to be heated to very high temperatures. So it just required our towers to be a little bit bigger, and that ended up increasing our capital costs. So basically, you can see the next following one would be the reactors, and then finally followed by our water recycle. These costs won't really change too much because it's kind of something that we can't really change too much about our process. So now that I've talked about IBL, I'm going to go a little bit further into the OBL costs. So OBL generally includes product storage, utilities, and site development. So these are capital costs of things that are outside the battery limit. So the OBL cost for our plant was $42.78 million. The biggest cost for our OBL, which you can see up on this pie chart, was our cooling water system, otherwise labeled a CT upgrade right here. The reason why this cost is so large is because we're using a ton of water throughout our plant to cool down a lot of streams. It's used in most of our heat exchangers, so it ended up being a pretty large cost. The following largest would be our product storage, and this one is also fairly large because we have a pretty large flow rate of styrene that we need to send out to the OBL and end up storing. So now that I've talked a little bit about capital costs, I'm going to go into the costs that we have to be able to pay all the time, which are our ongoing costs for our plant to operate properly. So our ongoing costs includes things such as waste, labor, raw materials, utilities, taxes, and other features which support the operation of the plant. So what you can see up on the board is currently our waste and our raw materials are the highest contributors to our ongoing costs. The waste cost was around 60% and the raw material was around 38%. Unfortunately, when we submitted our documents, there was actually an error in our calculation where our wastewater was entered in per years rather than per hour. So it ended up having us to have this really large waste cost. So the next slide that I'm going to show is the corrected cost. Basically what we did was we corrected for that per year into a per hour, and so I'm going to show what those costs are now. So our ongoing costs are more likely around $51.7 million per year, and it's all basically due to our raw material costs. It's followed by our fixed costs and our taxes, but they're pretty negligible compared to obviously the raw material costs, which you can see up on the board. So from now on, when any time that we're going to mention our original design, that was our documentations that were submitted. Those were the original calculations, and any corrected refers to when we fixed that error calculation. And now I'm going to hand it off to Paul, who's going to be talking a little bit more about our cash flows and ATRR.
Okay, first we're going to dive into our cumulative cash flow. You can see here that after the steady rate of our capital cost for building, we have this very large dip, which we can attribute to the mistake made in our original calculations with the error in our rainwater. But after the correction, we can see that we actually start to make money after our 3-year building pretty steadily until the end of our 18-year life cycle to get to a cumulative cash flow of roughly $1.2 billion, whereas we were mistakenly expected to make $4.7 billion. Moving on to our ATROR and our original and calculated present worth. We originally calculated our percent ATROR to be 5.3, which is much below the 20% ATROR that competing projects that Nitline Chemicals is considering are at currently. And we expected to have a negative present worth of around $1.5 billion. After our correction, we were happy to see that we were above the 20% by around 3.5% for our ATROR, and that our corrected present worth is actually $227 million. So looking at our required netback cost, originally we would have to sell our styrene for over double the market value in order to reach in percent ATROR that would compete with the other projects that Nitline Chemicals were considering. But after the correction, we found that we could actually sell it for 2 cents less than market value and still be at 21% ATROR. And now I'm going to send it over to Isaac, who's going to wrap up with our recommendations.
So for overall recommendations of the plant design, we evaluated the plant at our original values and also our corrected values. So when looking at our ATROR for our originally calculated values that were miscalculated, we got a 5.3% ATROR, but then our corrected values, we got a 23.4% ATROR, which is above the 20% specification that is needed. So along with this, as well as the 0.23 billion positive present worth at year 2036, and the break-even cash flow point at 2023, as well as the $1.2 billion cash flow at the year 2036, which is the end of our evaluation, because we evaluated the years from year 2018 to year 2036. We recommend that you proceed with the designing and building of the chemical plant for 1,3-butadiene to styrene. So along with that, we also have other recommendations for how to make the process a little bit more feasible. If we're going to do it again or just other things to expand on in the future. The first one being putting heat exchangers before the distillation columns. We found that the reflux ratio will be a lot lower if you put those heat exchangers beforehand, and this reduces the energy needed for the distillation columns, which will in turn create a lower cost for utilities. As well as we found that a high percentage of our costs, not only capital but operating, were due to the package distillation that we were purchasing and using. So if we were to model that and design it ourselves, yes, we would have more of distillation columns and things like that to separate the crude C4s into the 1,3-butadiene to go into reactor 1, but we think that there might be an option to design that a little bit cheaper than what we're paying for it currently. Another option would be to consider vacuum distillation for the columns, especially when separating ethylbenzene and styrene. Vacuum distillation is common among different industries, because it reduces the amount of polymerization for styrene in the column. Due to the column's high temperatures, you have a lot more styrene polymerization, whereas if you use vacuum distillation, you can run the columns at lower temperatures and still get the same separation. So this would, in turn, might be a little bit more expensive due to the vacuum conditions, but it also will improve the styrene flow production rate, because you don't have that polymerization in columns, and also the added headache that you get when you have polymerization throughout distillation columns. And lastly, another huge cost that we had to endure was the treating of our wastewater. Our biggest distillation column was for the wastewater treatment, just to make that a clean enough water source that you could emit it back into the environment without having to go through different regulations. So based on these 4 recommendations, as well as the previous slide and the greater than 20% ATROR, we recommend that the plant be built. Thank you for your time.